Attention here, no filtering on the.
No food. No food and drinks.
No food or drink to that, okay?
How are you?
Oh, okay. So. Oh, hello. Oh, yeah. How are you? Not too bad. Not too bad. We're gonna do a lab 2 right now. Yeah, I VIO and ILAs, like debugging tools. So that's what I'm gonna be covering.
Not like Mac.
How much longer should we wait until?
Yeah.
3 more.
2 more minutes. Okay.
It's really good quality. I bought it like 2019. And it's still good.
Oh, hiya. Hiya. I just want to double check. Do you guys have access to the lab 2 slides? I just uploaded them like 10, 15 minutes ago. Just want to make sure that you guys have access to that. It should be around there. Yeah, it should be. Yeah. Okay, perfect. Thank you. All right. Right. Amazing. Thank you. I'm officially still working here, but like unofficially, I'm like at Northeastern like 3-4 days of the week. So I'm still like working with Bipin and stuff like that on his things and stuff. So, but like occasionally I'm here just like for like TA work and stuff like that. And like also like if I just need to like do like paperwork things, I'm like here also. So yeah. Yeah. As of now, it's only just me and another one, Tan. I think that's it. Yeah, those are the only two. There's only two right now. The rest are postdocs. The rest are postdocs. Yeah. So because his most recent PhD just all graduated, became a postdoc with it now. So yeah, and yeah, but yeah, for the most part, it's basically postdocs. Okay, all right, all right, amazing. I can just do this one. All right, welcome back, everyone. Hope you guys had a good week break from hardware design. So welcome to the second lab session. In this session, we're going to be covering the debugging tools the VAIOs and the ILAs that are provided in the Vivado suite. And this will be really beneficial to your coursework. It'll make certain things, such as when we'll present next week on finite state machines, it'll make the debugging process for that a lot easier. So, but even before that, I want to also like do a little bit of prefacing in terms of kind of addressing some of the headaches I noticed that other people were encountering 2 weeks ago when we were doing lab 1. So I kind of want to cover that and make sure that most people here are on the same page. So just a bit of an overview of what we're going to be doing in today's lab. We're going to be just covering the common headaches that people have been having with Vivado. We're going to learn on an abstract sense what VIOs and ILAs are. We're going to modify the 4-bit adder project that we worked on 2 weeks ago to leverage these debugging tools. And then we'll also learn about ILA triggers. So this is probably, so I want to first cover what's probably the first headache I noticed when we were going around like 2 weeks ago. So one of the first headaches that I noticed in regards to the debugging in terms of using Vivado and stuff like that is in regards to the naming convention. In particular, a lot of people have been having headaches in regards to the spaces within the file names. Now, this isn't just addressed in terms of the file names, it's also included in the folder directories that you're included. So let's say that you were to save, you're not using your personal laptop, you're using the laptop provided by school, and you're saving it on your OneDrive. The way that OneDrive is set up has a space in the file name, and that is going to be what Vivado reads as well, and it's not going to be able to interpret that. So when you're saving files in Vivado, you want to make use, basically, you want to make sure that the entire directory, including the above folders that you save your project in, doesn't have any spaces. It needs to have alphanumeric characters, meaning A to Z, upper and lowercase, 0 to 9 numbers, and underscores. Those are the only characters that are permitted in saving the files. So that's headache number 1 that I just kind of wanted to address. And the second headache that I also know, I've not really particularly noticed, but I kind of foresee, or something I observed a couple of years ago, and also like last year iteration of hardware design, is in regards to the deletion of projects. So Vivado is very weird in this aspect. So if you were to delete, so let's say you want to delete your project, for example, in the File Explorer, Vivado is actually still going to see that project instance within itself. So it's kind of almost have like a phantom project. So just to kind of recap, so if you were to delete your project, the entire folder in the File Explorer, but you haven't done this in Vivado, Vivado is still going to register that that project is still there. So in order for it to make sure like that Vivado doesn't see it, you also have to delete that project folder within Vivado as well. So I can kind of show you what I mean with this. So if I were to go to Vivado here, I have, this is the main screen over here. If I were to, let's say I want to open a project, I would then have to go into the folder here, press delete, and make sure that this thing is deleted. So if you notice here, this debug 4-bit adder folder is here. And there are cases where, again, if you delete it in the File Explorer, it's not there. So you need to make sure that's happening. All right. So actually, before I go on, does anyone have any questions or any like tidbits and stuff like that they kind of have when using Vivado and stuff like that? If not, we can move on to the next stage. All right. Okay. All right. So for predominantly the first 30, 45 minutes, we're just going to be kind of going over the debugging tools that Vivado, some of the debugging tools that Vivado provide, primarily in regards to VIO and the ILA. So the VIO stands for virtual input and output. And what it'll allow you to do is to play around with your settings on your FPGA without interacting with the FPGA at all. So what I mean by that is, assuming if you guys did the 4-bit adder project 2 weeks ago, when you were playing around with the inputs and outputs, you had to manually move the switches, right? You have to turn it on and off. That's good in a sense for a 4-bit adder, but it doesn't particularly scale, especially if, let's say, in a project you need to make a CPU where you have a finite state machine. You can't particularly interact with these using switches, so you need to figure out another way in order to interact with it. And virtual input output, or VIO, is how you can do this. You can also, so it's much easier to scale your debugging. It's just a much easier way to debug. So the second one I want to talk about is the integrated logic analyzer. And this is very good when you want to catch the specific instances of when you have overflow. So in the specific cases where you have extraneous behavior in your circuit, that is kind of where you have your ILA. You kind of think of it as like a digital oscilloscope for your FPGA. So otherwise, you're going to be basically constricted to just using your LEDs, turning them on and off. And again, that doesn't particularly scale. Oops, sorry. Oops. All right. So just a bit of so what we're going to do is we're going to make this lab a little bit interactive. So these slides are kind of just like a bit of a record of what we're going to be doing this lab session. So, but I'm going to also be going through this manually using Vivado. So you have like a live demonstration of what is going on here. And also during the thing, I'm going to be also using some useful and helpful like shortcuts and stuff like that that'll make certain things in future labs and also the coursework a little bit easier. So okay, so first thing is a bit of a preliminary. So you guys can see the slides on the Keys page. So these slides, you'll all have access to this. It's on the Keys page. It should be under Lab 2 slides, is under the coursework section. So we can first start by manually importing the source code from the coursework in regards to the 4-bit adder. So we can just escape here. Let's go to the coursework page and let's download the Lab 1 4-bit adder. Make sure that's extracted. And we have the Lab 1 demo here. So now we're going to be creating a project. So we're going to be creating a project and we're going to preface this for Lab 2. We'll just call it the debug version of the 4-bit adder. So we're going to, from these zip files that we extracted, we're going to be importing this into the current project. Oh yeah, this session is recorded. Yeah. Yep. All right. So if we go into here, so you can basically just figure out where you want to save your whereabouts you want to save your lab. So let's have it go here. I'm just going to set it up. Make this the debug 4-bit adder, making sure the naming scheme is correct. So you've probably seen this screen before, and you probably are a little bit tired in regards to like figuring out the exact string that you need, like the exact part number that you need in order to select your thing. Useful shortcut here is if you were just to go under here, instead of parts, you go under boards. You have all the selection of the Vivado software here. And if you type in BASIS, which is the FPGA boards that we have, you are able to select it through here. So that will be able to select that. You can go next, and now it'll automatically register the part number, so you don't have to directly copy the string. You don't have to particularly know exactly which one that you have. So you can just basically use this as a bit of a shortcut in order to get to the board. So is any questions on that, or is it clear on that? All right. Okay, all right. So under here, we can then add the new design sources. So I'm going to be importing the new design sources in regards to where we have previously downloaded it. So I have imported these things. And just to preface, you do not have to import the test bench Verilog file in order for this lab, because we're going to be testing this manually ourselves. You do not need to make use of the test bench. All right. Okay, so once you have imported these files, or once you get to the step, you should have a hierarchy that kind of looks like this. So I kind of just want to have a little bit of an ask around. We imported 4 files. Why is it when we import the 4 files, all of a sudden we have 7? Why do we all of a sudden have like 7 files when in our hierarchy, in our project hierarchy now, when we only imported 4? Why is that? Okay. Yeah, kind of like this. It's not the Linux ones. It's if you were to look at the top.v file, you'll be able to piece together why this is the case. So you can kind of think of the top.v file as kind of, so I'm not sure if you guys are familiar with programming, you can kind of think of it as your main file. So, you know, in main, you have a main file, you can import different code files across to make things slightly easier. So if you were to look at top.v, this is where we kind of collect all of the project files together. So this is where we define our inputs, A and B, for the board. This is where we define our switches. And this is also where we define the other modules that we have also imported. So we define a module for the 7 display. And this is also where we define the full adder 4-bit. And if you were to look within the 4-bit adder, we call this 4 times. So it's when we call these 4-bit adders, we call the full adder 4 times is how we get the hierarchy. This is so basically, so Vivado is kind of reflecting kind of how much we have imported it. So it's kind of a little bit smart in the sense to kind of show exactly how it is. So it kind of reflects based on what you've written in your main file, what is going on in your hierarchy, what is going on in your design. So in case if you see a bit of a mismatch in terms of what you're importing, like, so what you're expecting in terms of how many components you have. So let's say here you have, let's say you expect it to have 6 bits. You're expecting to have 6 full adders, but then all of a sudden you only see 4. It's through this file hierarchy, you'll be able to identify why that is, so that you can go in the full adder and then basically define it here. All right, so with that out of the way, now I'm going to be doing the constraints. So I think this is something I noticed a couple of people having a little bit of an issue with. And I kind of want to preface this by saying that you can, so I'm not sure how familiar people were in terms of lab 1. So when you're doing the lab 1, you have to basically, once you do your synthesis, you have this pop-up, and you basically need to go through all of these different pins, declare each one of them, declare the voltages every single time. And that is a bit of a headache and is not particularly something you kind of want to repeat. So one thing you can do is, let me just highlight this again here. So I'm not sure if people are familiar with the screen that they have saw. So maybe if some of you tried lab 1, my guys might be a little bit familiar with the screen that you see here. So if you see this, you have to basically manually select each one of these every single time. Good news is, if you've already done this in lab 1, you can import the exact same constraints file into this project, and you don't have to worry about this again. So the way that you can do that is quite simple. You can simply do this by adding the constraints file going through your previous lab and basically just ensuring that you import that constraints file, and then now your new project, your lab 2 project, now has the constraints file that you did in lab 1, and you don't have to go through that entire process of defining the pinouts for every single one of your, for the pinouts for your entire board, and also the voltages for the board itself. So let me demonstrate that here. So I'm going to add a file here. So I have add or create constraints. I'm going to go to the 4-bit adder here. So you can find the constraints file. So if you've done lab 1, it'll be under the dot sources, constraints 1, new, and this is where your constraints file is going to be. And so if you've done the entirety of lab 1 and you did that entire pinout, it'll generate this file. You can import this directly, press finish, and now it's in your port, and now it's in your now it's in lab 2 project, and you don't have to worry about doing that entire process all over again. So basically, it just saves you a lot of time, saves you 5-10 minutes in terms of basically just manually setting the pins every single time. All right. So once you can finish all these steps, you should now have this following hierarchy in terms of your constraints. So you should have, in your design sources, you should have a top file. You should have underneath it 2 files, the seg7 display file, the full adder 4-bit, and then within the full adder 4-bit, 4 instances of the full adder. And when you go into the constraints file, you should now see this. So if you guys think I'm going a little bit too fast and stuff like that, you could always just like pipe up, say that you can slow down and stuff like that. If not, if you don't want to interact, you can also just go to the Keats page. There's the slides out there, and you can go through it. So it should be detailed enough for you to cover what's going on. If not, then yeah, you can send me an email, or you can also talk to me after the session in terms of where things are a little bit confusing. All right. All right. So the first thing that I want to cover is in regards to setting up the ILA. So the ILA is basically, we want to tell the ILA exactly what wires that we want in order to debug. So what are the wires that we want to be reading? What are the wires that we want to be setting in order to determine the behavior of our board? So the way we can do this is by simply just replacing the definitions of our wires and signals here to just simply have a flag to make sure that the debug flag is on, so that when we set up the ILA later, that these are the wires that it can be reading. So I'll be doing this now. So if I were to go to the top.v file, these are the wires and signals that I want to be correcting. So I can replace all of this with this code over here. All right, so with that done, so now we're basically just saying that for the debugger in the future, to look at wire C out, look at the result of the wires, the sum, look at C in, look at B, and look at A. We haven't told the debugger itself whether it's the input or the output, but we're basically just prefacing the debugger and just saying that, hey, you know, this is like something you need to pay attention to. So in the future, when we eventually set it up, they'll be able to know exactly which wires to look at. So that's the first. So that's basically setting up the ILA. So now we kind of also want to set up the VIO on the top file. So we want to basically set up additional virtual inputs which can control the FPGA. So ideally, in terms of debugging, we want to have the FPGA board. We want to be able to interact with the FPGA board. But also, if need be, we can also interact using our Vivado software to control the FPGA board. So we can pick and choose basically when we want to debug, what method we want to debug. So if we want to be very specific, we want to be quite physical with it, you can use the switches. If not, you want to kind of scale it up. Let's say you want to test something else, then you can test it on your computer. So it can basically do this by setting up a multiplexer with the virtual signals in Vivado and also with the switches on the FPGA board themselves. So we can do this by simply just replacing the code and the base 4-bit adder and the top.v file by replacing this line with this text here. So once we do that, we're basically just saying so when we do this, we're basically just saying that, okay, so now I'm declaring a virtual signal, VIO-A, VIO-B, and a virtual count-in. And then I'm also defining an input, a virtual input called VIO cell. So that's basically selecting whether we want to have our inputs be virtual through the computer, or whether we want it to be physical through the FPGA board. And so that's what the first paragraph here. And the second paragraph here is basically saying for the input for the FPGA on the board, it can either be dependent on VIO-A or on the switches, depending on the inputs, the VIO cell. So basically, whether VIO cell is on, make sure it's you take the virtual inputs. If the VIO cell is off or 0, go to the switches. So that's kind of what the syntax is for that one. Normally in the coursework, I'm not entirely sure whether we're allowed to actually use multiplexers like this in the coursework. I'm not sure. Are we? Okay. So we can use multiplexers like this in the coursework. But if not, you can also just still use this for debugging purposes. This is still quite good in order to have. So, but fortunately, you guys have it in the coursework, so you don't have to feel that bad in terms of using this. So now that we set this up, now what we have set up here in the code is that, okay, I have these wires here. We're setting them for debug, and I'm going to be talking to these things using either virtual signals or using the switches on our FPGA board. So now what we have to do now is to set up the VIO core itself. So at the bottom, basically you're just setting up the virtual signals. Basically, it's just a black box that's going to be generating the signals and simultaneously also reading it. So you can just basically just simply copy this code here. Okay. I can basically just copy this, and basically what this is going to do is basically just instantiate the VIO. So it's going to be talking to the FPGA. It's going to be telling the 4-bit adders, okay, so these are going to be my pins. So these are going to be the signals I'm going to be feeding you, and also is going to be reading the 4-bit adder, the 4-bit adder's outputs as well. So it's going to kind of think of it as a prepping of an oscilloscope here. All right. Oh, any questions on this so far? Is there any questions in regards to the syntax, in regards to Verilog? Oh, yeah, sure. Sorry? Oh, you see, add this code. So all this code that I showed you before, all of this code, you only have to modify this on top.v. You don't need to go to the seg7 display. You don't need to go to the 4-bit adder. Actually, not the 4-bit adder or any of the full adders. You can just modify this in the top.v file. Yeah, so right before the end module code. So because the end module code is basically signifying that's when your code is ending. So in the sense, you're just only touching the top.v file. So this makes things quite simple in terms of like adding stuff. All right. So now that we have this, we set this up in the top.v file, we actually need to add this to the actual project itself in Vivado. So what we can do here, we're going to be setting up the VIO core now. So before I even do that, notice when you added this code in the top.v, in your hierarchy, you now have this VIO module in the hierarchy itself. So the top.v file is in real time reading what you have in your top.v. Vivado's reading in real time what you have in your top.v file, but you actually haven't instantiated the actual VIO thing itself in your project. So now we're going to be doing that. And once we're done, we're going to see that that question mark that's next to the VIO is going to disappear. So what we can do is that we're going to be adding this to the IP catalog. In the IP catalog, we're going to type in VIO. So VIO virtual input output. So I'm going to double click here. And now I'm going to see this pop-up. So this pop-up is basically going to just say, okay, what is my configuration? How am I going to set it up? So a little bit of a pop quiz. Considering our 4-bit adder, we have A, B, and C in. And our output is going to be C out and sum. How many probes do we need? Input probes do we need for the VIO here? What's our input? How many probes do we need? It's 3. Well, there's one change that we did in this setup in this file. So we have, in terms of inputs, we have A, B, and C in, but there's also something that's determining where our inputs is coming from. So that added input is the VIO selector. So we have 4. So we have 3 corresponding to the adder itself, 1 corresponding to the VIO selector. And our probe count out is going to be, what is going to be our output here? Yeah, it's going to be 2. So let's double check here. So yeah, so here we're going to actually, oh, sorry, other way around. So the reason why it's the other way around is the following. We're reading, so the VIO is reading directly from the 4-bit adder. So the 4-bit adder is outputting the sum and the C out, which is what the VIO is going to be reading. So that's going to be the inputs. So it's reading the sum and the C out. So you need 2 inputs. But it is also simultaneously driving the 4-bit adder itself. So you need to have 4 outputs for the VIO. So the outputs for the VIO are driving the ALU and is simultaneously reading the output of the ALU. So it's kind of like a loop. So we want 2 input probes for the VIO, 4 output probes for the VIO. Now you then have to also select the width, since considering we're dealing with a 4-bit ALU, we are going to be dealing with 4-bit inputs. So a little bit of a pop quiz here. Considering that my output of my ALU is 4 bits, what's the width of probe in 1, probe in 0 of the sum? 4, exactly. And what is going to be the width of my C out? 1, exactly. Now for my driving signals, this is going to be a little bit more contrived. So I want to ask to this section here, considering I'm dealing with a 4-bit ALU and the output of the VIO is driving the ALU, what will be the width of the first output that's going to be driving A? Does anyone want to take a guess in terms of how, like, what it will be? What will be the width of A here? 4, exactly. So you have 4 bits. So this is basically determining the inputs of the ALU. So you need 4 bits for A, 4 bits for B. You have 1 bit for the C in, and I'm going to have 1 bit for the VIO selector, since basically you just only need it to be on or off. You don't need any more widths for it. So once I press OK, and also just for safety reasons, I'm going to set the synthesis options to be global. And when we generate this, the generation of output products is completed successfully. So now I will now have this module here. Now this is filled in. And now I can click into here. I can go in here, show the IP hierarchy. It's updating. I can go in here and read all of this goodness in terms of what it has set it up for us. I mean, of course, you can code this up manually yourself if you want. You can do this if you want, but I'm not going to give any bonus points in that. So basically, ideally, just have a value generated for you. So with that out of the way, now we can actually run the synthesis. And so now we have synthesis, so we can run this. And in the meantime, I'm going to be talking about the reasoning that we want a debugger. So can anyone, I'm going to kind of throw this, so I'm going to ask a question. Why is it that a debugger would be useful? Under what, like, what will be, let's say you're making a CPU, what will be certain circumstances that a debugger can be useful? Does anyone have any ideas? Yeah. Yeah, exactly. So you basically can use it to basically determine the wrong output, but a bit of an asterisk there is in regards to you can also figure out what exactly is causing your output, or was causing the extraneous behavior. So if you don't have any debugging tools, you're going to be observing that something is wrong, or worse, you don't even observe that something is wrong. Things are looking nice, but if in the inside you actually observe what's going on, you're you're basically using the wrong equations to get the right result, which can be fine under certain perfect conditions. But when the conditions are no longer perfect, everything is going to break loose. Everything's going to be a massive headache. And also, as in regards to that, that's also, again, where the debuggers become really helpful, is in that situation where everything breaks loose, at least you have some tools that's going to be able to help unravel what is causing this issue. So you can be able to peel back through the layers and understand what is the exact case scenario that is happening, that is driving the overflow to happen. So, right, so now that synthesis is now done, I can now move on to the next step. So if I'm going to open the synthesized design, I'm going to ignore that. The first thing I'm going to notice, so let me go to the tools, or let me go to layout, IO planning. I'm already going to have all of these things already defined, ideally. But if they're not defined here, don't worry. You can go to your sources, go in your constraints, and you can make sure that all of these things have already been defined for you. So I'm going to go back to the schematic here. Now we're going to be setting up the actual debugger itself. So what we're going to do here, let me go to the next slide. So we're going to go under tools, and we're going to set up the debug wizard. So we're going to select the debug wizard, and now we are going to basically see this window. Because of what we typed in top.v, it's going to now be automatically register some of the wires that we have written before. But in case ideally you want all of the wires set up, if you don't, no need to panic. You can manually set this up yourself. So you can here, you go actually under here, you find the nets to add. You go here and you type in sum. So you can import this here. Since we're missing cout, I'm also going to add this here. There we go. And now we have all the nets that we're going to be using for the debugging. So basically this is now talking to all of the wires within the ALU, and this is basically when we're running the ILA, when we're running the digital oscilloscope, is going to be reading all of these wires. If we were not to add those two wires, it's not going to be reading the sum and the C out, which is actually the things that we really want to see. So now we can basically just finish this. We can skip through this, finish. And now what we're going to have, we're now going to have an updated synthesis. Let's put cancel here. So if we're going to go here, I'm going to press save. Make sure after this step, make sure to save. If you close it, it is not going to remember that you set up the debug. And also make sure to select this within the existing constraints file, so that when you save this, and you go into your constraints file, not only do you see your pinouts for your FPGA board, and when I reload this, you're now also going to see some added code that is now corresponding to the debugger. So this constraints file is basically telling the FPGA, hey, and these certain pinouts, I have set up the debugger tool here, and I'm going to be reading the pinouts here. So of course, again, you can avoid these steps by just manually coding this yourself, but the Vivado is pretty nice in the sense that you can do these steps using the user interface, and it's going to automate all this code for you. Otherwise, you would have to do all this writing, all of this codes, all these set properties manually, which is not going to be particularly nice. So considering we have this, now we can run the implementation. Here's the steps. Now not only do we need to, can we run the implementation design, we can actually just generate the bitstream in itself. So let me go back here. Actually, I'll just finish this. Let's have this finish. And actually, in the meantime, let me open the synthesized design. I kind of want to highlight the advantage that comes with this design, or the advantages like you have when you go under Vivado. I'm not sure if you guys remember, in regards to these different pop-ups, you can actually see manually what is going on in regards to the circuitry of what your design is. So this is not isolated in regards to the 4-bit adder circuit that you made. This even includes the debugger that you added itself. So you get to see the circuitry of your 4-bit adder, but you also get to see the circuitry of your entire design, including with the debugger. I'm just kind of waiting here just to wait and see for the implementation to be done.
And it's cool.
I think that's with her. So. Okay. So now that's generating the bitstream. We can kind of just relax and stuff like that. But does anyone have any questions in regards to certain concepts, certain like things with Vivado you're kind of having a little bit of headache with? If you want, just raise a hand. I can come around and we could have a little bit. Yeah. The synthesis failed for yours?
Like often.
Oh, okay.
Like the ports
Um,
and everything.
Actually, I'll have Zihao help you with that. Yeah. Zihao, he has help with needs help with the synthesis.
Sure.
Right. All right. So now that the bitstream generation is now done, I can now open the hardware manager. And here I want to make sure you guys have the FPGA. Once you get to this step, eventually, you have connected this to your FPGA board. And you're going to see that no hardware target is open. You can open the target here. I'll have it auto connect. And now I'm going to program the device. And now when we program the device, we're going to see these two pop-ups. If you haven't reached this step, that's fine. It'll be fine because then you can basically just see what's going on here. So you're going to see these two different pop-ups here, and you have these two different tabs. So the tab here on the left is your ILA. So this is going to be your oscilloscope. This is how you see your waveforms of your 4-bit ALU. And here is where you define your virtual inputs and outputs. So if I'm going to press plus here, I'm now going to see all of the wires that I have defined here. So I'm going to be importing all of these wires in here. And now here you can also do a little bit of selection. You can kind of configure your virtual input outputs to behave how you want. I'm going to set mine to be an LED. Just to let you know, you can configure this by right-clicking on the thing. So I'm going to set the low value here to gray, here to red. I'm going to have the sum here, the text, but specifically unsigned decimal. I'm going to have the same for here. Same for here. I'm going to configure these two to be buttons. All right. So when you program the device, you're going to have the following. So I'm going to be able to play around with the switches here on my board. But when I'm going to play around with here, if I put the selector here, I can also play around with my circuitry here. And I don't even need to talk to the board. So I don't even need to interact physically with the board. I can talk with the computer here. I'll set it to 8. And it's also going to be controlling the board here. So I don't need to interact with any of the switches. I can basically just talk to the software here. And it's also going to be controlling my output here on my board. Oh, yes, thank you. Yeah. So I can play around with the thing here. So let me set this to be ceiling. Is I think ceiling camera. Oh no, I don't think so. Actually, let's see. It's a little bit weird. Anyway, technical difficulties aside. Anyway, you should be able to play around with your FPGA board and basically play with the switches. Yeah. Oh, the VIO. Oh, so if you don't have that, did you program the device? Yeah. So you only see that. So yeah, if you generate the bit stream and you go to the Open Hardware Manager, I should have added that in the slides. You are not going to see the VIO. You're not going to see the ILA. When you program the device, then you're going to see it. And just to walk through the steps again, if you go to the VIOS tab on the here, you get to press the plus, and then you can control the thing. So let me play around here. Thank you for setting it up. So let me let's put it here. All right. So let's say I want to, let me select this to be 0. I'm going to reset both of these just for clarity's sake. So I can play around with the switches here. I can do my debugging. I can basically input to my ALU what's going on here, even see my overflow with what I have physically, or I can actually go into my computer here. Let me turn the VIO cell on, And now I can derive these signals on my Vivado. So let's say I want to add, let's say I want to add 6 with 8. Now I'm going to get 14 is going to be reflected on my FPGA board, but it's also going to be reflected on my output thing here. So I'm going to be able to read both. So this in itself is fine, but ideally we want to be able to see the exact cases when we have overflow. So we can also, let's see, we can run this thing here. You can also see the waveform is being triggered here. I can zoom out. Let's make this a little bit bigger. I can kind of see what's going on in the waveform thing here. But let's say I want to see the waveform of when, let's say I only want to see the waveform of when I reach overflow. Otherwise, I'm not particularly interested in seeing the waveform. So the way I can do this is by setting up what's called a trigger. I can set up an ILA trigger, and that's basically going to turn on the ILA or to display the waveforms only when a certain condition is set. So if I were to go to, you set it up by going in this window here. Actually, let me, can I full screen this? Yes, exactly. Yeah. All right. Let me go back here. So if you go under trigger setup, I'm going to press plus, and I'm going to be setting this dependent on the cout. So here I can specify what conditions I need in order for this waveform to be displayed. So I'm going to be setting this as an equal sign and setting this as, oh, thank you. I hope this is not going to be a feedback thing. But anyway, so then I'm going to be able to set this to be, I can set this to a logical 0. Ideally, for this case, I would like to set this as a 0 to 1 transition, because otherwise, if you were to set this on a logical 1, basically every single time you reach overflow, this waveform is going to be displaying. You don't particularly need that. You only want to see how that overflow got reached. So in that case, you can just isolate that to be on the 0 to 1 transition when the cout goes from a 0 to a 1. So in that sense, I can now, since I have this set up, I'm now going to run this, and now I'm going to play around with what I have here. So let's say I'm adding 6 and 8. I don't have any overflow. Let's say I'm going to be adding 10. Actually, let me add 13. Now I'm going to have overflow. And now I'm going to see what case has caused this overflow to happen. So I can see I had originally 6 and 8. I'm adding it together. I'm getting E. I can actually change this to be unsigned decimal to make this a little bit clearer. Like so. So I'm adding 6 and 8. I'm getting 14 here. But then all of a sudden, I'm adding 6 and 13. Now I'm getting 3, which is not only the wrong answer, but I'm also getting an overflow here, and it's displaying exactly when that is happening. So now let's say I want to have another condition. Let's say I only want to see it. Actually, let me reset here. Let me set this back down to 8. No, let me set it to 3, sure. So now I'm only interested in when both cout is on and when the sum is equal to 0. So in that case, then I can add another condition here, set this to sum. Then I'm going to have this operator equal to 0. Let me set this to unsigned decimal, set that to 0. And I want to make sure as I go into this pop-up here and say that the set trigger condition to global AND. So if I were to set this to OR, that basically means if either of these conditions are satisfied, then trigger the waveform graph. But if I only wanted to show the waveform when both conditions are satisfied, then I'll set it to global AND. So now I will reset this. Now I'm going to play around with the settings here. Let's say I'm adding 6 plus 3. I'm going to be adding 6 plus 8. And now I'm going to be adding 6 plus 10. And now look at that. I have overflow. And now I'm going to be seeing this condition here. Versus if I were to add, let's say, let me reset this again. Let me add 6 and 11. I still have overflow, but it's not reflecting here. And let me set it back down to 10 again. And now I get the thing showing again. So, gosh, it didn't even show there. But anyway, basically that point stance is basically in the sense you can set multiple conditions in order to set this ILA to turn on. Now, that's kind of it for the second lab, but basically I kind of want to, and this is probably not the best circuit in regards to demonstrating why a debugging is quite bad, is why a debugger is really useful in this case. It gets much more useful when the project becomes a lot more complicated. Your coursework is going to be setting up a RISC-like CPU on your board. You're not going to be able, you only have 16 switches, you only have 16 LEDs, they can only provide you so much information. So what you want to do is to make the debugging, make your life way easier when certain things are not behaving the way you want it. So in this sense, this is really helpful in that, because considering next week, where you're going to be dealing with finite state machines are kind of like a black box. You can't particularly interact with it when you have an FPGA. It's kind of hard for you to see, based on the LEDs, what is the current state of your finite state machine. Let's say it's in an infinite loop. You're not going to be able to identify that just by simply looking at the board. You can only identify that, in a sense, by using tools provided here, using VIOs and using ILAs. So that's kind of it for the lab 2. If you guys have any questions here, I can bounce around. I think we can take a 5-ish minute break, 5 minutes break. So then we could talk about, or 5-10 minute break. So then we could talk about the second part of the coursework in regards to Datapath. All right. No worries.
Oh, the lab demo.
Yeah.
你们开始。
OK， before we get started to task 2 of our coursework. All right. Hope you are doing well for task 1. So because we are going to need everything wrote in task 1 in our task 2. And task 2 is about Datapath design. I think the lecture, Haiyu has already tell you about the Datapath and single cycle CPU design. So we are not as far as that. For this task, it's just a simple Datapath with your ALU and shifters. So let's get started. To build a data path, you need a register file. A register file is basically a small but fast memory structure inside the CPU that stores the temporary data and operands for the instructions. The role of data path, it supplies the operand to the ALU for arithmetic and logic operations. They also stores intermediate results and frequently used variables. It interfaces with the instruction decoding stage for the register addressing. So this is the structure of our register file. It has 8 registers and 16 bits for each register. So what's inside a register file? To build a register file, you need a multiplexer first. This multiplexer also comes with a decoder because you only need to read from 8 registers. That means you only need 3 bits to represent them. However, in order to build your register, you need a 3 to 8 decoder. That decoder helps you to identify which to decode the binary codes to a 1-hot code, and this 1-hot code will identify which is exactly the register. Here's a quick example. I put my clocks on the registers, and when the clock comes in, all the registers should update when you try to write to the register file. So in order to write to the register file, you need the data written into the registers. And we also need a write num decoder because you need to know which register to write. And for each register inside this register file is a register with enable. That means only the enable signal is 1. The register can successfully take the input numbers. So when you try to write in the register file, you put the data you want to write on the data bus, which is data in, and put the register number on write num. Note, it's only 3 bits because you only have 8 registers. And when the clock goes high, the data is written to the exact register that you try to write in. So far for the writing procedure of the register file, does anyone have any questions? Yeah, I think the register file should be quite easy to implement. And also, I will provide you the register file we're going to use. So this lecture is basically just to understand what's inside the register file. Let's have a quick example. Writing a 5 into register R0. R0 basically register 0. So when you try to write a number, you prepare this data on the data in bus, and you provide the address to the write now. So the decoder will decide which register to write, just like this one, and it will you will have a write signal to tell the reg file that I am going to write in the register. And when the clock comes in, the register will update based on current signals. So after this clock, the output value of this register will also be 5. Another example, trying to write 7 into R1. So I prepare my data, and I prepare the address, which is 1, and the decoder will decode to the exact register I want to write. And I give a write signal, it will end to the decoder to tell which register to write. And then the clock comes in, the data is successfully written into register R1. Now I try to read from a register, which is pretty easy. I just simply provide the read num, which is the address that I want to read. For example, in this case, I'm reading R0, so I just give it is 3-bit 000, and the decoder will decode to a 1 hot code. The 1 hot code will decide which register as the data output. So this is the 1. This one goes to the register R0, and this is a combination logic. So there's no clocking. The data is directly sent out to data out. So why only 8 registers? Because for all computer architectures, smaller is faster. And the reason is the delay increases with the length of wires. Generally, all the other things are just being equal, prefer computers to be faster. So for arithmetic instructions in the simple RISC machine, all the operands must be in the register file. The other IS, they don't make the same choice, like x86, ARM, etc. But just this is what we are doing here. So Datapath example with registers, I think you already have idea about how to read the instructions. For example, I'm trying to add R5 from R1 and R2, and add R6 from R3 and R4, and then I make a subtraction to from R5 and R6 and write back to R0. So this is our risking data path. A quick overview here. Inside here, this is the register file we just talked about, and on the right is the shifter and the ALU that you should have already prepared from the last task, because you are going to use it in this task. Okay, and on the left side, we have 2 inputs. They are datapath in and SXIM8. This SXIM8 basically refers to sign extended immediate value 8-bit. And we have a multiplexer here from a vCell, just like what Stefan did previously. You have to select between the datapath in and SIMM8. So quick overview. Inside this datapath, you have all these control signals, which is vCell, RF, REN, WEN, which means write enable. And you also have a shift OP, which is the operand for the shifter that you designed from the last task. And on the right side, you also have another 2 multiplexers. One is A cell, one is B cell. These select the A operand and B operand that goes into the ALU. So you're not just calculating the data from the register files. You can also select 2 out source. One is simply 0. You can see if A cell is 1, you are selecting 16-bit zeros, which is just a pure 0. And for the B cell, you can see there's a SXIM5, which means sign extended immediate value 5 bits. This data will come from the operands, but we are not going to talk about it for this task. On the right side, you have another two registers. These are the output registers. The one is the data pass out. Basically, it's the ALU results. Another one is the status. The status is a 4-bit 4-bit signal that contains the output the status of the outputs. Here's the multiplexers. Multiplexers are purely combinational logic, as we mentioned, because it's just a switch to switch between the two signals. And these are the ALU and the shifter you have already designed in the earlier task. You should directly make an instantiation in this task. And these are the registers with enable function, because load Y and load S, they are basically enable functions to tell the register, to enable the register to take the signal from the ALU. And from C to assembly, in the last lecture, we have covered some C to assembly language converting. So machine cannot read C code, obviously, and C code must compile to assembly language first. Each instruction takes between 1 and 4 cycles in execute. Each cycle contains certain control signals asserted to perform required operations. The problem is which control signal are asserted depends on which instruction is being executed. A decoder and a state machine will drive this signal at the right time. You will design this part in lab task 3, which is the FSM for the CPU. In this task, I'm going to show you a quick demo about this quick C code, which A equals to something, B equals to something, and you perform C equals to A plus B. And finally, you have D equals to C. And if you try to compile them into assembly, it's just a simple 4 lines of code. So the first code to execute, which is move R3 into an immediate value 24. So register R3 should contain 24. So how do you do it? We can do this in one cycle. So this is it. I prepare this 24 into the immediate value right in. And the VCL goes to 1, which means I'm selecting SXI MM8 as the input. And then I give RF write enable a 1 to tell the register file I'm going to write this number. And the write address is going to be 3 to tell the register file that I'm going to write a number to register 3. So once a clock comes, this data will be successfully written into R3. So next cycle, we're going to execute the next instruction, which is move in R5. The number is 13. So again, we can finish it in one cycle, which is like this. So next part is a little bit hard. The RISC-king CPU is not a single cycle CPU because you see the registers in the data path. That means you have to finish this instruction in multi-cycle. So for cycle 1, we read R5, R3 into our operands. And in operands data path, we have the shifter, we have the A cell and the B cell. We have to make them in the right way, so it goes to the right. So the right number goes into ALU. So this happens in one cycle, and at this cycle you have to set load Y and load S to be 1 because the result, which is 37, will be written into ALU out in the next cycle. So next cycle, we set our write 2, R in 1, load Y equals to 0, load S equals to 0, because we want to keep the register data, the output registers, to make sure they maintain the results. And VCL is going to be set as 0, so the data pass out goes back to data pass in, and the data is written back to register 2. So you spend 2 cycles to finish these add instructions. And finally, we try to move R7 into R3. So this is where all the A cell and B cell comes important, because you don't want to perform any like add instructions. but you have an ALU in between. So the only thing you can do is try to pass through this data from R3 to R7. The way we do it is at A cell, we select 1. So the A operand will be 0. So 24 add 0 is still 24. So you have the right data comes into the data path out. And in the second cycle, we just send the same data back to register 7. So this is the way you move the data in between the registers. So this is the top structure of our task 2. In task 2, you are going to write the data path, which is everything you see here. But in this lab, we will provide you a demo project on FPGA, so you can try the data path yourself. Okay, so basically this is going to be the data path you write. And this is going to be the top file I will provide. With this top file connected in this way, you can use the switches and push button to control the whole data path. And the 7-segment display will show you the data path output. So this is the top structure and lab structure for task 2. Do you have any questions for now? Do you have any question about what you are trying to do for this task? If no, I'm going to show you a quick demo. I'm going to program this task 2 into a FPGA, and I'm going to show you how to control your data path with switches and push buttons.
Like the first one too.
Yeah.
Done, yeah.
I'm going to show them the demo. All right. I have my project ready, which is everything is ready, and I'm going to write the bitstream into the FPGA. So you have a quick idea playing with it. All right, a review about our data path. As you can see, this is going to be the module that we are going to write, which is the data path. And inside the data path, you have all the modules like what we've shown in the slides. And on the top, I have prepared these registers, the top registers for you, and the 7-segment display. So everything comes out from the data path out will directly shown on the 7-segment display. All right, one tricky thing is happening? Yeah, this is the headache situation again. Never put your project under OneDrive.